Hello and welcome to Quantitative Chemistry, so GCSE exam questions. So this is obviously about all calculating things in chemistry, so you might need a calculator to follow along with this. So you are allowed a calculator in a chemistry exam, there's no non-calculator in your science. Okay, so these are taken from real exam questions and they're from different papers, so the numbers, like the number of the question might be a bit different. Okay, so example, this is question 5 from a paper. Transition metals have many uses. The pie chart in figure 6 shows the use of one transition metal. So we've got numbers here, 7% transportation, 3% coins, 65% electrical equipment. I mean, I would guess this is copper. So calculate the percentage of this transition metal used in construction. So it's just, I get my pen icon to come up. So let's have this. Right, I think using, right, so we've got obviously 100%, must be the whole pie. Okay, minus, I'm going to add them, so 65% plus 7% plus 3%. Okay, so we're doing a calculator. I'll do my calculator. So 65 plus 7 plus 3 in brackets, like how I've written it, 25. Okay, nice, easy to start off with. Figure 7 shows 5 statements about iron. Put ticks in the boxes in figure 7 to show which statements are true and which statements are false. The first one has been done for you. Iron is a poor conductor of heat. Okay, so false. Iron can act as a catalyst. Yes, that's true. Iron forms compounds that are coloured. So I think about rust, it's like red. Planet Mars is covered in rust and it's pretty sort of pinky red. So true. Iron has a low density. No, false. Iron has a very high melting point. So it's one of the transition metals that's going to have it. Yeah. Okay. So 3 marks. That's quite a nice question. Most iron produced is converted into alloys of iron. State why alloys have more uses than pure metals. So alloys, it's like a mixture, contain 2 or more metals with the beneficial properties of the 2 or more metals, rather than just one. Okay, we've got something to work out here. An alloy of iron contains 0.4% molybdenum. Calculate the mass of molybdenum contained in a 30-gram sample of this alloy of iron. So again, this is a maths question. So how would we do this? So 30 times, so to get 40% would be 0.4. To get 4%, it would be 0.04. So to get 0.04, you go 0.04. Okay, so we just need to do that on our calculator. So it's just, again, just another calculation. So 30 is going to my calculator times 0.004. And we put equals 0.12. It's going to be a small number, isn't it? Because it's a small sample. 0.12. So it's just a maths question there. An ore of iron is mostly iron oxide, Fe2O3. Iron can be extracted from this iron oxide by heating it with carbon. Balance this equation for the reaction that takes place. Okay, so it's a balancing equation. So Fe2O3, something carbon, something iron, something carbon dioxide. Remember, on the left has to equal what's on the right. Okay, so sometimes this is a bit of trial and error as well. Okay, so we've got 2 ions, so we'll start with that. 2 times 2 here, though, so it must be 4 iron, okay, to equal here. Right, how many oxygens have we got? 2 times 3, so 6 oxygens here. So to equal this, we need to do 3. 3 times 2 is 6. So that gives us the carbon then, doesn't it? 3. So actually, that's not as bad as it first looked, is it, that one? Most copper ores are described as low grade. This means that the percentage of copper in the ore is very small. 5,000 kilograms of one copper ore was found to contain 42.5 kilograms of copper. So that's not very much, is it? Calculate the percentage of copper in its ore. So again, this is a maths question. So it's a bit like saying someone got 70 out of 100 on a paper. So it's 70 divided by 100 times 100. If it was like 70 out of 90, it'll be 70 divided by 90 times 100. So in this case, same thing. So 42.5 divided by 5,000 times 100 to get a percentage. Okay, again, that's another calculator thing to do. So just type that into a calculator exactly as we have it. So 42.5, sorry, 4.5, reset that. 42.5 divided by 5,000, it's going to be quite a small number here, isn't it? And then we times it by 100, 0.85%. Okay, so yeah, low grade means there's not much of the metal in the ore. So it might not be economical, so it might not be worth the money, okay, to actually dig that up, okay, and process it. It's a low grade ore. A titanium ore was analysed and found to contain 12 grams of titanium atoms combined with 8 grams of oxygen atoms. Calculate the empirical formula, so empirical means by measurement or by experiment, of this titanium compound. The relative type masses, titanium 48, oxygen 16. Right, so you must show your work in titanium ore. So empirical formula, so you've got 12, let's write this out a bit, like a ratio, good to do ratios. This is titanium, Ti, this is oxygen, O. So 12 to 8. So let's work out in terms of moles. I always think this is the best way of doing it. There are other ways, but I think this is the best way, easier to follow it anyway. So moles, so we've got formula or atomic mass, because you've got atoms or formula. Oh, sorry, I just don't have enough room there. So moles is actual mass, so I didn't leave enough room there. Mass divided by formula mass, atomic mass. Okay, to work out how many moles. So mass, so we're going to go for titanium first. So 12 divided by 48. Okay, so that's going to be a quarter, so 0.25. Again, you can use your calculator to make sure. You don't have to be great at mental maths for this. Just obviously that I've seen that equation many times. Okay, so remember this hasn't got a number. This is just moles. So it hasn't really got a it hasn't got a unit yet. Right. So for oxygen, so this is titanium. Oxygen. Mass 8 grams. Oh, I should put grams there, shouldn't I? Okay, divided by 16. So 8 divided by 16, so we're going to see that's going to be 0.5. Okay, remember this is a ratio. So the ratios now, okay, which we could have kind of seen a bit before, couldn't we? It was, so titanium to, let's write out here again, make it a bit clear. Titanium to oxygen. So we've got 0.25 titanium to 0.5 oxygen. Okay, so we need to have something with at least sort of whole numbers in it, is what I'm trying to say. So timesing it by 2, we'd get 0.5 to 1. We need to times it again, as long as you do it to both sides, 1 to 2. So got 1 titanium atom to 2 oxygens. So it's TiO2. So yeah, you might have to do a few of those to get kind of used to it. They're actually not that bad once you get used to it. They don't usually give you very difficult numbers with that. And yeah, you are allowed to calculate. As long as you know how to do it, you're okay. The sodium sulfate solution, so this is from another question, but this is the maths part of it. The sodium sulfate solution was made by dissolving 28.4 grams of sodium sulfate in water to make 250 centimeters cubed of solution. So it's the same in water, 250 milliliters, but that's only for water. Calculate the concentration of this solution in grams per dm cubed. Give your answer in 3 significant figures. Right, so concentration. So let's think about this. There's a 2-part thing, it's got 3 marks. Think about the units of concentration. So it's mass divided by volume. Okay, mass divided by volume. So if they did, initial one, if they did 28.4 grams in 250 centimeters cubed. Right, so let's do 28.4 divided by 250 would be quite a low. So 0.1136, I read off my calculator, grams per centimeter cubed. Okay, so solution grams per dm cubed. Okay, so dm cubed. Let's think about what a dm is. So dm is a decimeter. So it's a cube. It's always a good thing to actually draw this because it helps you remember. Decimeter is the amount of volume in a 10 by 10 by 10 cube. So centimeters. So 10 times 10 times 10. So 10 times 10 is 100. And then times 10 again, so 100. So it's just a litre, isn't it? Okay. 1,000 centimeters cubed. So all we have to do is do 28.4 grams divided by 1,000. Okay, so 28.4 divided by 1,000. 0. It's actually kind of easy in the first question. 0.0284 grams per decimeter cubed. That was actually nice and easy. Gram per decimeter cubed. Okay, let's go on to the next one. After evaporation, the mass of the potassium chloride was determined. The theoretical yield of the experiment was 0.7 grams. The actual yield was 0.84. This gave a percentage yield greater than 100%. Calculate the percentage yield of this experiment. Oh, okay. So, when we work out percentages, so remember this is going to be more than 100%. It's unusual to see this. Okay, so we're going to have 0.84 divided by 0.7 and then times 100. It's unusual to see it greater, but maybe there'll be a reason, obviously we'll talk about. 0.84 divided by 0.7 times by 100, 120. Okay, it's just a reason why the actual yield was greater than the theoretical yield. So usually it's less, isn't it? But there could be contaminants. So the evaporation, the evaporate, I should say, could be contaminated or not all the water has completely evaporated. Could be some water still left. Okay, so another bit of maths in this chemistry. The concentration of carbon dioxide in the atmosphere can be measured in parts per million, ppm. Figure 1 shows the measurement in January 2018 and 2019. Okay, so we've got January 2018, 407.96. January 2019, 410.83. Calculate the increase in concentration in ppm of carbon dioxide from January 2018 to January 2019. Give your answer to the nearest whole number. So it's just taking one from the other, isn't it? So 410.83 minus 407.96. So 410.83 minus 407.96. Right, that gives us 2.87. But we were asked to put it to the nearest whole number. So the nearest whole number is 3. Give a possible cause for this increase in concentration of carbon dioxide. So it could have been a rise in the burning of fossil fuels. Okay, that put CO2 into the atmosphere. Okay. A catalyst contains cube-shaped nanoparticles. Another bit of maths here. Figure 3 shows a diagram of a cube-shaped nanoparticle. The length of each side of the cube is 9 nanometers. Calculate the surface area of the cube in nanometers squared. So it's not the volume, as that's what it looks like you're going to do. Okay, so surface area. So one side, so how many sides? So a cube has got 1, 2, it's got 6 sides. Okay, so, and each side, so each face, each faces, that's the best way, faces. So each face is 9 by 9, so 81. It's got 6 faces, so it's 81 times by 6. And we can use our calculators for this again. Remember, it's the surface area. Okay, 81 times by 6, 486 nanometers squared. Okay, so thank you for listening to this video. So there's lots of bits of maths and chemistry, and usually papers are 20% maths. So good luck on your exams and keep practicing all the maths questions here. So thank you very much, and hope to see you in another video.